When ultrasonic waves are used in medicine for diagnostic purposes, high-frequency sound pulses are produced by a transmitter and directed into the body. As in sonar, reflections occur. They occur each time a pulse encounters a boundary between two tissues that have different densities, or a boundary between a tissue and the adjacent fluid. By scanning ultrasonic waves across the body and detecting the echoes generated from various internal locations, it is possible to obtain an image or sonogram of the inner anatomy. Ultrasonic imaging is employed extensively in obstetrics to examine the developing fetus as seen here. The fetus, surrounded by the amniotic sac, can be distinguished from other anatomic figures so that the fetal size, position, and possible abnormalities can be detected. Ultrasound is also used in other medically related areas. For instance, tumors in the liver, kidney, brain, and pancreas can be detected with ultrasound. Yet another application involves monitoring the real-time movements of pulsating structures, such as heart valves, known as echocardiography, in large blood vessels. When ultrasound is used to form images of internal atomic features or foreign objects in the body, the wavelength of the sound wave must be about the same size as or smaller than the object to be imaged. Therefore, high frequencies in the range of 1 to 15 MHz are the norm, where 1 MHz is 1 × 10 to the 6th Hz. For instance, the wavelength of 5 MHz ultrasound is lambda equals V divided by F, which equals 0.3 millimeters if a value of 1,540 meters per second is used for the speed of sound through tissue. A sound wave with a frequency higher than 5 MHz and a correspondingly shorter wavelength is required for locating objects smaller than 0.3 millimeters. Neurosurgeons use a device called the Cavitron Ultrasonic Surgical Aspirator, or CUSA, to remove brain tumors once thought to be inoperable. Ultrasonic sound waves cause the slender tip of the CUSA probe to vibrate at approximately 23 kHz. The probe shatters any section of the tumor that it touches, and the fragments are flushed out of the brain with a saline solution. Because the tip of the probe is small, the surgeon can selectively remove small bits of malignant tissue without damaging the surrounding healthy tissue. The Doppler flow meter is an interesting medical application of the Doppler effect. This device measures the speed of blood flow using transmitting and receiving elements that are placed directly on the skin. The transmitter emits a continuous sound whose frequency is typically about 5 MHz. When the sound is reflected from the red blood cells, its frequency is changed due to the Doppler effect because the cells are moving. The receiving element detects the reflected sound, and an electronic counter measures its frequency. From the change in frequency, the speed of blood flow can be determined. Typically, the change in frequency is around 600 Hz for flow speeds of about 0.1 meters per second. The Doppler flow meter can be used to locate regions where blood vessels have narrowed, since greater flow speeds occur in the narrowed regions according to the equation of continuity. In addition, the Doppler flow meter can be used to detect the motion of a fetal heart as early as 8 to 10 weeks after conception.